In our previous step, we have covered our much needed important steps on how to cover up or how to follow our given problems over there, or how to solve this given torque voltage analogy over there. So let us do that, or let us solve our given problems over here. So first step is quite naturally our nodal form of diagram. So we do require to go for that consideration. Okay. As I have followed those important steps over there, so I am just going to show you the step-by-step methods on how to follow those important steps over here. So the first one is our how to consider our nodal form of diagram over here. In order to do that, we just do require to point out the first we do require to point out the much needed angular displacements over here. So we have got three displacement parameters over there, which are theta 1t, theta 2t, theta 3t. So how to convert this given conventional mechanical rotational diagram into our much needed nodal form of our diagram over here, that is very easy. So first we do require to place our much needed consideration or much needed angular displacement for our mechanical rotational system over here. So we have got three different angular displacement parameters over here, which are theta 1t, then comes theta 2t, and the next one should be our theta 3t. Okay, so the next step will be what are the important blocks or elements that are connected with this angular displacements over here. So I can see that the theta 1t is connected with our j1. So I'm just going to include over here. So the first moment of inertia j1, that is been directly associated or connected with our theta 1t. So I have connected over here, and under this solid surface over here, the rotational frictional coefficient of our v1, that is also been present over here, and that is been connected with our theta 1t over here. So we are going to connect over here. So this is our b1. So this is quite naturally our b1, and for our next step we can see that the in between our theta 1t and theta 2, so theta 2t, so this is our theta 2t, we have got the spring element or the rotational spring element of k1 that is been present over here. So in between our theta 1t and theta 2t, we are going to connect our k1 over here. So this is our k1 that has been connected over here, and just go for that consideration. The theta 2t is directly associated with our j2 over here. You can see that the j2. So we are going to connect the j2 at the nodal point of our theta 2 over here. So this is being considered as our j2. Okay, so the next part is once again the frictional coefficient of our rotational element of b2, that is being associated with our theta 2t over here. So once again we are going to connect our b2 over here. So this is our b2. We are going to connect over here. This is our b2. So just move on towards our right hand side for our diagram. We can once again see that in between our theta 2t and theta 3, we have got the another spring element of our k2 that is been present over here. So in between our theta 2t, theta 3, we are going to connect our k2 over here. So this is our k2 that has been connected over here. And at the last part of our consideration, what are the elements that is been connected with our theta 3, we are going to show you over here. So the theta 3 that is been connected with our j3 over here. So this is our j3. And last but not the least, the frictional element of B3 that is been present over here. So we are going to include our B3 as well. So this is our B3. Okay, and on the extreme left hand side, the torque has applied on our theta 1t over here. So we are going to include the torque element of our consideration, and that is been connected with our or that is been associated at the angular displacement of our theta 1t over here. So the torque is directly associated along with our theta 1t over here. So the applied torque is this one. So this is the process on how to convert this conventional diagram into our much needed nodal form of our diagram over here. I just do require to make sure that this type of considerations are absolutely crystal clear for your consideration. I'm just going to follow up our consideration on how to convert this given conventional diagram into our much needed nodal form of our diagram over here. So first, do consider our three different nodes of our consideration, or three different angular displacement parameters that has been present over here. These are our theta 1 t, theta 2 t, theta 3 t over here. So I have just first considered our theta 1 t, theta 2 t, theta 3 t over here. So the next part will be what are the elements or what are the much needed blocks that are connected along with this theta 1 t, theta 2 3, theta 3 3 over here. So we do require to find out that connected blocks over here. So I can see that theta 1t has been connected with our G1. I have included the G1, and the rotational fictional element of our B1 that has been present over here, and you can see that in between our solid surface and our rotational block, the frictional parameter is quite naturally present over there. So I have connected the B1 with our theta 1t over here. You can see that. Just move on towards our right hand side of our consideration. The at our theta 2t, the J2 is been placed over here, and in between our theta 1 and theta 2t, the K1 spring or rotational spring element that has been present over here. So in between our theta 1t, theta 2t, the K1 that has been connected over here, and quite naturally the theta 2t is been connected with our J2 block over here, and quite naturally the another frictional parameters are coming to picture that has been associated with our theta 2t over here, and that has been called as B2. So we have connected the B2 with our theta 2t over here, and at this part of our consideration, the theta 3 is connected with our J3. So this has been connected with our J3, and the B3 is placed at the extreme right hand side for our consideration, and in between our theta 2t and theta t3, the K2 is been present over here. And after all of these things, so we do require to find out what is the applied torque portions over there, and at the extreme left hand side for our circuit consideration, we have realized that the torque element that has been connected, or that has been directly associated with our theta 1t over here. So this is the ultimate process to convert our conventional diagram into a nodal form of a diagram over there. So in our next step, we do require to apply the D'Alembert principle at our node 1, node 2 and node 3, and we after I have applied that D'Alembert principle, ultimately we will get the much needed D'Alembert principles over there, or much needed formulations or much needed differential equations over there, and quite specifically that equation will be our mechanical equations. So just wait for my next part. Always do remember that this type of basic considerations or basic formulations or analogies are very important for our consideration, and only engineering brothers can show you this detailed type of analogies over here. So what are you waiting for? Please do follow our videos and do subscribe our channel, and if you still have any doubts, please let us know in the comment section for better understanding. Do like, do share our videos, and keep following our channel. Just wait for my next part. In our previous step, we have completed the formation of a nodal diagram over there. Just in this present consideration, we do require to apply the D'Alembert principle on our node 1, node 2, node 3 to have the mechanical differential equation over there. So let us go for that consideration. As we have got a very little bit amount of space over here, so I'm just going to write down the first equation over here. So just by applying, we should say that this is our node 1 and this is our node 2 and this one will be our node 3. Just by applying our D'Alembert principle on our node 1, what we have got? We have got the equation as the applied torque minus, what is the meaning of a D'Alembert principle? The D'Alembert principle is applied torque plus resistive torque, and the summation of that two opposing torques, the ultimate resultant value of that torque will be 0. So in this present diagram, we have got the applied torque as tau t, and what are the resistive elements over here? The resistive elements are, these are our blocks. So let us just do include over here. So this one will be J1 d2 theta 1 t divided by our dt2, and the b1 is been associated over here, which is minus b1 d dt of our theta 1 t, this one minus our k1, this one will be, as we have taken that the 1 is our reference factor over here and k1 is being placed in between our 1 and 2 over here, so quite naturally I should say that theta 1 will be greater compared with our theta 2t, which is k1 multiplied with our theta 1t minus of theta 2t, which is ultimately equal to 0. So this will be our first equation over here. Now if you do rearrange our given equation, ultimately if we do transfer our all those resistive elements to the another side of our equation, and the torque portion will be placed at the another side of our equation, so the equation will become this one. So this will become equal, and all these part of our consideration will become our plus. So this is our first given equation over here, and just by following the same procedure over here, just by applying the D'Alembert principle on our node 2, we have got, if you do apply the D'Alembert principle on node 2, we do require to follow that what are the elements that are connected with our node 2 over here. So we can see that the J2, B2, K1 and K2 will be placed over there. So we have got 4 elements that are connected with our theta 2 over here, and quite naturally we do require to include that just by applying our D'Alembert principle over here. And you can see that all those parts that are connected with our node 2 are all resistive elements for our rotational system over here. So if you do apply the D'Alembert principle over here, all those resistive elements are or have got the negative sign over here. So the absolute answer will be our minus J2 d2 theta 2t divided by our dt2 for this one. The b2 that has been connected with our theta 2t, so quite natural, minus b2 d dt of our theta 2t. This is our second part, and in between our 2 and 1, let us go for that, minus we have got our k1 multiplied with our theta 2t minus of theta 1t, which is theta 2t minus of our theta 1t, and quite naturally the k2 which are placed in between our theta 2t and theta 3t, which is minus k2 multiplied with our theta 2t minus of our theta 3, which is equal to 0. Now if you do take the minus common from our both of our resistive elements over there and do transfer to the another side of our equation, the equation ultimately will become, all these elements will become our plus. So this will be plus, this will be plus, and this will be plus, and this will be plus. Okay, so this is our second equation over here. And as we have got very little bit amount of space over here, and I should number as should give the number as, this is our equation 1 and this is our equation 2 over here. So I'm just going to note down our equation 2 over here because we have got very little bit amount of space over here, and in our next stage we do require to apply the same procedure just by applying the D'Alembert principle upon node 3 to have our last equation or last differential equation for our mechanical rotational system over here. So to have our more space, I just do require to rewrite our equation 2 in this smaller space over here. So the equation is our J2 d2 theta 2t divided by theta d theta. So as we can see that we have got less amount of space. So this is our one way to write down our equation 2 over here, plus our b2 d dt of our theta 2t for this one, plus once again k1 multiplied by theta 2t minus of theta 1t minus our theta 1t, this one is been constructed, plus our k2 multiplied by our theta 2t minus of our theta 3, which is equal to 0. So this is quite naturally our equation 2. And as I have noted down our equation 2 over here, so I can erase this part of our equation and once again do follow up the same procedure just by applying the D'Alembert principle on our node 3 to have our third differential equation over there. So let us just go for that consideration, and before I go into that, I should do require to change or check our given equations over here, which is k1 theta 2t minus of theta 1t plus k2 theta 2t minus of theta. So okay, so this has been properly arranged over here. So I can erase this given equation 2 over here. So at the top of our consideration, we have got our equation 1. In our lower part of our small space over here, we have got our next equation, which is our equation 2. And at the next stage, if we do apply the D'Alembert principle on our node 3, what is going to be the equation? The equation will be this one, which is minus J3, as the same procedure, what are the elements that are connected with a node 3? So we can realize, or we have seen that the J3, B3 and the K2 that are connected over here. So without wasting any time, if you do apply the D'Alembert principle on a node 3, we have got our next equation over here, which is minus J3 dt of our theta 3, this one, as we can see that J3 has been connected with our theta 3 over here, and the next part will be minus B3 d dt of our theta 3, this one, and the last one, the K2 has been connected in between our theta 2t and theta 3 over here, minus our K2 theta 3 minus of our theta 2t. This will be ultimately equal to 0. Now if you do transfer the minus from our given equation, and if you do transfer to the another side of our equation, so all this minus equation will become our plus. Okay, so this is ultimately our given third equation over here. So this is the exact way, or this is the next stage to get our mechanical differential equation over here. So first we have completed just by forming our conventional mechanical rotational system diagram into our into this diagram over here, and in our next stage, after just I have applied the D'Alembert principle on a node 1, 2 and 3. If we do apply the D'Alembert principle on node 1, we have got this equation 1, and if you do follow the same procedure just by applying the D'Alembert principle on our node 2, we have got this is our second equation, and if we do follow the same procedure just by applying the D'Alembert principle on our node 3, we have got this is our third equation over here. So we have got three differential equations over here, and the three differential differential equation from our mechanical rotational system is being considered over here. And in our upcoming stage, we do require to try to convert this mechanical equation into an electrical one over here. That will be our next point of our consideration. But before I go into that, I want to give you some amount of time to think about it and think in a deeper way to keep on understanding our considerations. So you can do feel that no other YouTube channel will do like to give you this detailed analogies over here, and only engineering brothers can do that. You can do feel that. So what are you waiting for? Please do follow our classes, do follow our channel, do like, do share our videos, and keep following our channel. And always we try to connect with our larger audiences. So keep on encouraging your friends, or just give these specimen videos towards your friends, or towards your engineering relatives. They can do feel or do understand this type of depth of this knowledgeable videos over here, and only engineering brothers can do that. So please do support us, do follow our classes, do follow our channel, and you can do feel that this type of rigorous analysis are absolutely free, or that is been already available on our YouTube platform. So without following any other coaching classes or anything like that, just do follow our engineering classes. That will be the best way to start the preparation for your competitive exam. So just do follow our classes, and do subscribe our channel. That is the only way we can do connect with our larger audiences. So what are you waiting for? Just keep on following these smart videos and do follow these classes. So just wait for my next part.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.